Hello, welcome back to the second course of physics. And in this lecture, we will be dealing with dielectrics, and we will conclude the discussion on electrostatics by this lecture. The contents of this lecture will include an introduction and the definition of polarization, the electric susceptibility, the electric displacement, and to begin with, we have to recall that when matter is introduced in an electric field, or in other words, if an electric field is applied to matter, then movement or rearrangement of charges within the matter occurs due to the interaction of the charges with the electric field. So we have some sort of separation and rearrangement of charges. In metals, because the electrons are free to move, so if we apply an electric field, the electrons will keep moving freely until the electric field, the total electric field inside the metal is zero, which implies that if we apply an electric field on a material, on a body, then the rearrangement of charges within that body sets up an opposite field to the applied one. And in a metal, it is very obvious that at a certain point, the total electric field is zero and the movement of charges stops under the influence of the applied field. In non-metallic materials, however, only a slight net displacement of the charge within each molecule or atom of the non-metallic material occurs, and the macroscopic effect of this separation, charge separation, is observable due to the large number of atoms or molecules that exist. So although the separation is tiny within each molecule or atom, but we can observe a net macroscopic phenomenon correlated with that displacement and separation of charges. In 1838, Michael Faraday has found that during his work on electricity, that a non-conducting matter, if placed between the plates of a parallel plate capacitor, it causes the capacitance to increase just by due to the introduction of the non-conducting material between the plates. The specific inductive capacity, which is the factor by which the capacitance increases, is given by K is equal to the ratio between the capacitance after the introduction of the non-conducting material, C prime, divided by the original capacitance with free space in between the plates. And this C prime over C, this ratio, which is K, is found to be greater than 1, which implies that the introduction of a non-conducting material between the plates increases the capacitance. And this factor K is commonly used, is commonly known as the dielectric constant. So the dielectric constant of a material is simply the ratio of the capacitance when the material exists between the two plates of the parallel plate capacitor to the capacitance without the existence of the material. That defines the dielectric constant of the material. The name dielectric is actually due to the effect of decreasing the electric field by a factor of 1K as an effect of this dielectric material. That's why it's called dielectric. It decreases the field. The macroscopic electrical properties of matter can be described by the permittivity of the material. The permittivity of the material, epsilon, is defined as the dielectric constant K times the permittivity of free space. So, and this can be seen from the previous definition, C prime over C, and if we use the simple case of parallel plate capacitor and use the definitions of C prime and C, and use epsilon instead of epsilon naught in the case if when we have a dielectric in between the plates, we notice that this also defines the dielectric constant K is equal to epsilon over epsilon naught, where epsilon is the permittivity of the material and epsilon naught is the permittivity of free space. In other words, K, the dielectric constant, can be viewed as the relative permittivity, the permittivity of the material relative to the permittivity of free space, epsilon over epsilon naught, sometimes called epsilon sub r, relative permittivity. The vacuum, accordingly, can be viewed as a dielectric medium with K equals 1. So it can be somehow seen as a dielectric also. Now we move to the concept of polarization. When we apply an electric field, the material is polarized due to the separation of charges. And we consider, to begin with, a non-polar material, which is not polarized to begin with. The charges are not drifted from one another. And we consider a homogeneous material. Locally, it has the same density, and isotropic, that does not depend, the properties do not depend on the direction and locality. In this case, the dielectric molecules are designated by spheres with nonpolar structure. So there is no shifting in the charges, and the total charge is 0. Now, if we apply an electric field to the material, then each molecule, the electric field will affect each molecule and will exert force on the charges. So it will separate the charges from each other, and it will shift the positive charge to one side and the negative charge to another side. And the two charges, the two ends, which are charged by positive and negative, the separation between the two charges, positive and negative, could be termed delta. So delta is the distance between the two charges separated by the electric field in a given molecule or dielectric atom. Due to the influence of the electric field, due to the force applied to the molecule, there are charges Qi and Qj that are induced on the ith molecule or atom due to this application of the field. So this separation of charge induces a charge Qi on one end and Qj on the other end. And we can view that Qi is equal to minus Qj. It's the same charge, but on one side it's positive and on the other side it's negative. So let's keep in mind that Qi is equal to minus Qj. Now the net separation of the charges delta sub ij between the ith and the jth charges on a molecule is simply the position r sub I minus the position r sub j, the position of the first charge minus the position of the second charge. That gives the charge separation, or the distance, as a vector. Now, the induced dipole moment, we have defined the dipole moment before. The induced dipole moment, due to the charges I and j, which are the negative and the positive charges on one molecule, is by definition P sub ij as a vector is equal to the charge qi, which is considered, this is the positive charge qi, times delta sub ij. And this is simply qi times ri minus rj. And if we introduce, instead of qi minus qj, then this pij is equal to qi ri plus qj rj. qj is equal to minus qi. This is the definition of the dipole moment on one molecule in terms of the charges, the negative charge and its position, and the positive charge and its position. So we can add up all the dipole moments in order to get the total dipole moment in the material. And the total dipole moment is the summation over all charges multiplied by their positions over all the charges in the dielectric or in the material. This gives cursive P, the total dipole moment in the material. And now the charge separation, it is worth mentioning that the charge separation delta is really, really small. And this can be viewed because, this can be seen because if we consider, for example, a proton, a nuclear proton, and the charge separation is, the amount of charge separation is of the order of the electric charge on the proton. So we consider the electric field of a proton, a distance 1 angstrom from that proton. The electric field is of the order of 10 to the 11 volts per meter. That is the electric field introduced by a single proton charge E at a distance 1 angstrom from that proton. So thus, if the polarization of the charges within a molecule introduce even a very strong electric field of the order of 1,000,000 volts per meter, this the separation responsible for this 1,000,000 volts per meter is of the order of 10 to the minus 5 angstrom by simple argument, which is equal to 1 femtometer, 10 to the minus 5 angstrom. That means delta, the separation, even by a very strong field, like 1,000,000 volts per meter, introduce a very, very small separation delta of the order of 1 femtometer, which is of the order of the size of the nucleus itself, actually. The net effect, however, of the polarization is a macroscopic, because if we have a macroscopic dielectric, the separation between one phase, which is which would be charged negatively, and the second phase, which would be charged positively, is a distance that can be measured macroscopically. And now the polarization, P, capital P, is the dipole moment per unit volume of the material. So on a macroscopic scale, the interior of the dielectric remains neutral, because we always have equal number of positive and negative charges. That means the charges reside on the surfaces. Thus, polarization charges, as we say, appear on the faces perpendicular to the applied field. Those are the polarization charges appear on the faces of the dielectric. And these charges, if we assume that they arrange themselves as a surface charge density sigma prime, So the polarization charges Q prime is equal to simply the area of the face times the density of the polarization charges. And it's either positive or negative. It's positive on one side, negative on the other side. And the net dipole moment, accordingly, if we consider this material, the net dipole moment is simply cursive P is equal to the total charge, which is sigma prime times A, that's the total charge on one face, on the positive face, let's say, times the distance between the two charged faces. That gives the total dipole moment, and thus the polarization, which is the total dipole moment per unit volume, the dipole moment per unit volume. So we divide the cursive P, the total moment, by the volume of the material, which is AD. If we divide P cursive by AD, we get the polarization in the material is simply equals to sigma prime. So that means the polarization due to an electric field is simply the surface charge density. And thus we also recall that the surface charge density is negative on one side and positive on the other side. If one face now we have considered in the previous example the two faces are perpendicular to the electric field. If one face is not perpendicular to the electric field, so what happens? We have a perpendicular face, which is of area A, and we have an oblique face. An oblique face, the area of it is A over cosine theta, where theta is the angle between the electric field and the normal to the oblique face. Thus, the area of the oblique face is bigger, as we notice, is bigger than the perpendicular area. And the perpendicular area A is the projection of the oblique face in a perpendicular direction to the electric field. In this case, we have on the left side of the shape, on the perpendicular face, we have sigma is equal to minus P, and on the right-hand side, the oblique face is charged with a positive charge. Sigma prime is equal to P times cosine theta. And this can be viewed by a simple argument that the charge density on the oblique face is simply equals to Q prime, the same charge on the perpendicular face or on the oblique face. It's the same charge, Q prime. But in this case, the density is lighter because that charge is distributed over a larger area. So sigma prime on the oblique face is Q prime over the area of that oblique face, which is A over cosine theta. That means sigma prime is equal to simply in the oblique face to P cosine theta, which is lighter, which is smaller than sigma on the perpendicular face. That means if the face is oriented at some angle with respect to the electric field, then sigma is reduced by a factor cosine theta. Theta, as we mentioned, is the angle between the field and the normal to the face. So now, in general, if the polarization is a vector, if we consider the polarization as a vector, and that vector is parallel to the applied field, then the general term for the surface density is sigma prime is equal to simply the polarization P dot n hat, where n hat is a unit vector normal to the area, to the surface area, and P is the polarization vector. If the dielectric is now cut into two parts, then two new surfaces are produced, and those two new surfaces, if they are oblique in general, they make angle theta with the electric field. then there are charge densities, or a positive charge density on one area, one surface, and a negative charge density on the other surface, and the charge density on either surface has a magnitude of p cosine theta, as this figure shows. So cutting the dielectric into two parts will introduce two new surfaces with two different charge densities. If we put it together, then there's nothing is new, and the positive and negative charges on the new faces, they cancel each other, and we get the original configuration as having a negative charge to the right side of the block of dielectric and positive surface charge on the right-hand side. If we have a non-uniform polarization, the total surface charge on the dielectric is Q prime is obtained by integrating the surface density, which is P dot n, integrating it over the surface of the dielectric. And Q prime is thus viewed as the flux of the polarization vector through the surface bounding the dielectric by looking at the definition from the integral. Thus, if the polarization is non-uniform, such that the integral over the closed surface area is not zero, so the charge the charge that is arising from the surface distribution, if it is non-zero, then charge neutrality, because we know that charge is conserved. You cannot create or annihilate charge. So charge neutrality and the conservation of charge will dictate that we should have a volume charge density. If we have a net surface charge density, that means we should have a net volume charge density of the same quantity, magnitude as the net surface charge, and opposite in sign, which means that if I integrate over the volume of the dielectric, in this case, rho prime d tau, and d tau is the element of volume of the dielectric, and we integrate over all the dielectric, we should get a charge that is equal to the surface charge and opposite in sign. So it should be minus integral over the area surrounding the dielectric P dot n dA prime, and that is integrated over the surface of the dielectric. The densities sigma prime and rho prime are variably known as the induced charge densities, or the polarization charge densities, sometimes they are called, and sometimes they are called the bound charge densities. These are different names. And now we move to speak about the electric susceptibility, another concept that is relevant in this field of dielectric behavior. And we here mentioned that the net polarization is calculated from the sum of the individual molecular dipoles. So if we look at the material as consisting of individual molecular dipoles, and we consider the moment of each dipole, and we add up all of these moments, we will get the total polarization, or the total moment. After that, we divide by the volume of the material, and we get the total polarization. So thus, the total polarization is simply P, capital P, is equal to n times small p. Here, small p is the dipole moment of a single molecule or atom of the dielectric. And n is the number density, is the number of molecules per unit volume. So that way we have a moment per volume, and a moment per volume, total moment per volume in the material, is the description or the definition of the polarization. And as we mentioned, n is the density, number of molecules per unit volume. Now we define the local field applied to a polarized molecule, and this local field is defined as the field arising from the charges minus the field induced in the molecule itself. Here, E naught is the field, is the external field applied locally at the location of the molecule, which is arising from free charges. E prime is the field introduced by the external charges, but it is due to bound charges. Here, then E naught plus E prime can be called E, the external field, the total external field, external to the molecule, but it is now distinguished into two parts, one coming from the free charges, like in metals and so on, and one from the bound charges, like the surface charges or the volume charges in a dielectric, minus E submol, E submolecule, which is the molecular field. This is the local field at the location of a given molecule. And the induced field, as we mentioned, the induced field is the total field induced or the total field arising from the volume charge density and from the surface charge density of the dielectric. Of course, if we have a uniform homogeneous case, then with a uniform polarization, then these integrals are zeros. The local field is the necessary field, thus we can, by the definition, to maintain the equilibrium state of polarization of the molecule. So as we apply a total electric field E naught plus E prime to a molecule, there is a separation of charges within this molecule, and this separation of charges is in such a way that it introduces a molecular field that is in opposite direction to the applied field in order to maintain this charge in separation and charge in equilibrium state of the charge configuration. So if we assume that Hooke's law applies, so when we apply an electric field, the electric field will introduce a separation between the charges, which is delta, and in this case, the force applied is Q times E local, the local field applied in the location of the molecule, divided by K, where K is a spring constant. So K times delta is equal to the force applied, and this is Hooke's law. And thus, the moment P is equal to Q times delta, which is Q squared times E local over K, the constant, the spring constant sort of. And this is simply a constant alpha times the local field strength. And alpha is the polarizability here. And alpha is equal to Q squared over K from this definition, from this equation. This defines the polarizability. Thus, the polarization is simply P is equal to N times alpha in parentheses E minus E molecular, where E is E naught plus E prime, we recall. This is a relation between the polarization and the total field introduced by all the charges surrounding the molecule. This requires, the polarization requires the computation of the field due to the molecular dipole. That is necessary to calculate the relation, or to determine the relation between the polarization and the space electric field, E. The field due to the molecular dipole, which is necessary to determine this relation between the polarization and the spatial electric field, can be evaluated. And for simplicity, we assume that we have a spherical molecule of radius r, and there is no charge density inside the molecule. So all the charges are on the surface of the molecule. Now the polarization of the molecule inside the molecule is simply its moment, small p, divided by its volume, 4/3 pi r cubed. This is the polarization, the molecular polarization. And this would give the value of the surface density, charge density on the molecule, which is, as before, simply the polarization times cosine theta, which is simply small p, the moment, divided by the volume, 4/3 pi r cubed, times cosine theta. This is the surface charge density. And this shows that for theta smaller than 90 degrees, the charge density is positive, and for theta larger than 90 degrees, the sigma is negative from this formula. And the molecular dipole field is thus equals to minus, in the opposite sign to the applied field, minus 1/4 pi epsilon naught times the integral from 0 to pi small p cosine theta over the volume of the molecule, 4/3 pi r cubed, times 2 pi r squared sine theta over r cubed times r cosine theta d theta I hat. This is simply 1/4 pi epsilon naught sigma times dA times the area over r squared. And this is minus 3 times the moment p over 8 pi epsilon naught r cubed times the integral, it's just simplifying, from 0 to pi cosine squared theta sine theta d theta. If we perform this integral of cosine squared theta sine theta d theta, and from 0 to pi, we obtain the result as the E molecular field is equal to minus the moment of the molecule divided by 4 pi epsilon naught r cubed. This is a relation for the molecular field in terms of its magnetic, of its electric dipole moment P. And now multiply through by the number density, we get n times the molecular field is simply equals to n times small p, which is capital P, which is the polarization, divided by 4 pi epsilon naught r cubed, with a minus sign in front. And we use the previous relation for the polarization. We get the polarization is equal to the number density times alpha times the field E, spatial field E, minus the molecular field. And we substitute in this relation for the molecular dipole field, and we rearrange the terms, and thus we get the polarization in the material is equal to the number density times alpha, the polarizability, over 1 minus alpha over 4 pi epsilon naught r cubed times the electric field E, which is simply E naught plus E prime, the electric field introduced by the free charges and by the bound charges on the dielectric. And this relation defines this new quantity that we are after, which is the electric susceptibility. And the electric susceptibility is defined simply as N alpha over epsilon naught times 1 minus alpha over 4 pi epsilon naught r cube, which is simply the same constant in the above equation that's multiplied by the electric field E, but divided by epsilon naught. It's the same constant divided by epsilon naught, if we notice that. And thus, the relation between the polarization and the macroscopic spatial field E can be derived directly from the previous argument and from the previous examples, from the previous equations. We get the relation: the polarization in the dielectric is equal to epsilon naught times the susceptibility, electric susceptibility chi sub E, times the macroscopic field E set up by all the charges surrounding the location or the molecule in the dielectric. Now, considering this relation and all the definitions of all parameters, indicates that if the size of the molecule is known, then we can determine the polarizability alpha and the polarization P and the molecular field. We can calculate and determine all of these from the knowledge of the susceptibility of the material and the applied field. So if we know the susceptibility of the material and the applied field to the material, and if we know the volume of the molecule, the size of the molecule, we can calculate all these parameters: the polarizability, the polarization, and the molecular field. Now let's move to the electric displacement as another concept here. If we use Gauss' law, imagine that we have a dielectric and we draw a general Gaussian surface, which is this red surface, that cuts the dielectric somewhere, cutting a volume V prime. We assume that it has a volume charge density rho prime. We assume that the dielectric is polarized with a uniform polarization P, and the normal to the surfaces at the different points are shown here by n hat. A prime is this surface that is the intersection of the Gaussian surface with the dielectric. A1 prime is the surface of the dielectric that is enclosed inside the Gaussian surface, and A is the Gaussian surface. These are the definitions. With these in mind, we use Gauss law, and we say that E dot dA, if we evaluate E dot dA over all the area of the Gaussian surface, this should be equal to all the charges enclosed within this Gaussian surface divided by epsilon naught. And if we divide these charges into two types, the free charges Q naught plus the bound charges, which are due to the polarization, divided by epsilon naught, and having in mind that the polarization charges Q prime is equal to the polarization P dot dA prime evaluated over A prime. That is the only surface that is enclosed with surface charge density on the dielectric, plus the volume charge density rho prime d tau. This is integrated over the volume enclosed within the Gaussian surface V prime. And this is the most general argument, whether we have uniform polarization or non-uniform case. And this gives Q prime is equal to the integral of the charge density P dot dA prime over A1 prime minus P dot dA prime over A1 prime plus A2 prime. That is the surface surrounding the volume. So we replace the volume density integral by the area integral. and the previous argument, and this is equal to simply minus integral over the whole Gaussian surface of P dot dA. Thus, Q minus Q prime is simply, we substitute for these quantities, is simply equal to epsilon naught times the field, macroscopic field E, plus the polarization dot dA, which is simply equal to Q naught, the free charges. And now we define the electric displacement, and the electric displacement D vector is defined as epsilon naught times the macroscopic field plus the polarization. But with this definition, we reach a conclusion that the integral of the displacement, electric displacement dot dA integrated over the Gaussian surface is simply equals to the free charges enclosed within the Gaussian surface. So this is a new formulation of Gauss law in terms of the electric displacement and the free charges. In terms of the electric susceptibility, D is simply equals to epsilon naught times the macroscopic field plus the polarization. We substitute for it as epsilon naught chi sub E times the macroscopic field E, which is equal to epsilon naught times K, the dielectric constant, times the macroscopic field E, and this is by definition epsilon, the permittivity of the material, times the macroscopic field. And this gives a relation between the dielectric constant and the susceptibility as K is equal to 1 plus the electric susceptibility of the material. And as before, the permittivity of the dielectric material, epsilon, is equal to epsilon naught, permittivity of free space, times the dielectric constant K. The differential form of the equation we can get from the integral form D dot dA is equal to Q naught. We convert the surface integral into a volume integral. D dot dA is equal to div D d tau. And notice that Q naught is simply the integral of rho d tau, and that gives div D is equal to rho naught, or div epsilon E is equal to rho naught. So the divergence of the displacement in space, locally in space, at any point in space, is simply equal to the free charge density in space. At this point, I would like to finish my lecture and thank you for your listening.